For over a century, condensed matter physics relied on a strict binary to classify collinear magnetic solids. Every material was a ferromagnet or an antiferromagnet. This animated diagram shows a 3D lattice of a classic ferromagnet. In real space, its atomic spins align, creating a macroscopic magnetic field. In reciprocal space, the mathematical map of electron momentum, this alignment breaks time reversal symmetry, splitting the energy bands into two distinct spheres for spin up and spin down electrons. Antiferromagnets operate entirely differently. In real space, their atomic spins alternate perfectly, resulting in exactly zero net magnetization. Because the structure is perfectly compensated in real space, time reversal symmetry is preserved in reciprocal space. The electron bands are spin degenerate, meaning the spin up and spin down energy levels occupy the exact same state and collapse into a single sphere. This strict binary dictated a specific assumption. If a material has no net magnetization, its electron bands must be spin degenerate, rendering its magnetic state completely invisible to macroscopic electrical probes. But recent mathematical models predicted an anomaly. Equations described a crystal with perfectly compensated alternating spins that still produced a time reversal symmetry-breaking band structure. The math described a perfectly compensated crystal where electrons behave as if they are in a strong internal magnetic field. This represents the third phase of magnetic order. Physicists missed this phase because the standard mathematical models, relativistic magnetic groups, tightly bind physical space transformations to electron spin transformations. The anomaly was only found by applying a different framework, known as nonrelativistic spin groups. This mathematical approach completely separates the physical crystal lattice from the spin space of the electrons. By decoupling them, researchers could calculate the effects of applying independent physical operations to the atoms without forcefully rotating the spin axes at the same time. This revealed an entirely separate geometric relationship. To perfectly map the spin-up sublattice onto the spin-down sublattice, you do not have to slide or invert the lattice. You can connect the opposite spin sublattices strictly through a physical rotation. Identifying a crystal that requires this specific rotational symmetry is the strict mathematical criteria that separates an altermagnet from a standard antiferromagnet. Metallic ruthenium dioxide provides the clearest physical case study for identifying this rotational symmetry in a real crystal. Throughout the entirety of the 20th century, physicists measured its zero net magnetization, and they categorized it as a standard antiferromagnet. This animated diagram isolates the central ruthenium atoms inside the unit cell. Notice how a simple translational shift along the axis perfectly connects the spin-up sublattice to the spin-down sublattice. Because the magnetic atoms map to each other with a simple physical slide, the antiferromagnet illusion held up to scrutiny. However, that strict structural analysis ignores the critical presence of the non-magnetic oxygen atoms located inside the exact same unit cell. Once the oxygen atoms are factored in, their physical placement completely blocks that simple translational shift. The standard antiferromagnetic symmetry is destroyed. With translation and inversion mathematically broken, there must be another valid symmetry operation to map the opposite spin sublattices onto one another. The only non-relativistic operation remaining is to rotate the fully assembled crystal 90 degrees around its central axis, combined with a spin flip. The precise placement of the non-magnetic oxygen atoms forces this strict rotational relationship. That rotation is the defining physical signature of an altermagnet in real space. We can project that physical geometry into reciprocal momentum space using the Brillouin zone, a 3D mathematical boundary containing all possible electron momentums inside the crystal. The critical physics question is how a strict 90-degree rotation in physical space restricts the distribution of energy bands in momentum space. Because the opposite spins are linked exclusively by rotation, the spin-up and spin-down energy bands cannot maintain perfect overlap across the entire map. This split-screen diagram illustrates the mapping. Along the flat nodal lines, the spins remain completely degenerate, protecting the material's zero net macroscopic magnetization. But as the momentum vector shifts 45 degrees, the geometry forces the spin-up and spin-down bands to physically split. The magnitude and sign of this splitting alternate precisely with the momentum direction, which creates a highly specific, repeating anisotropic pattern. Physicists classify this highly specific energy pattern as D-wave spin splitting. This effect does not rely on weak relativistic spin-orbit coupling like the Rashba effect. It is a massive, non-relativistic spin splitting generated directly by the crystal potential itself. In materials like ruthenium dioxide, this non-relativistic spin splitting reaches nearly 1 full electron volt. That matches the internal forces of strong ferromagnets like iron or cobalt. The complex mathematics of the D-wave Fermi surface allow a zero magnetization crystal to process electrons exactly like a conventional ferromagnet. This abstract D-wave band structure translates directly into measurable macroscopic spintronic phenomena. Because of the D-wave splitting, altermagnets successfully break time reversal symmetry internally, removing the need for any net magnetization. Looking at this 2D schematic of electron flow, we see the longitudinal effect. Applying an electric bias along the anisotropic axis of the split Fermi surface makes spin-up and spin-down electrons travel at entirely different group velocities. This velocity difference generates a massive spin-polarized current. But apply that same electric bias diagonally by 45 degrees, and the material acts as an electrical spin splitter. The forward charge current loses polarization, actively driving pure spin currents outward at sharp transverse angles. This transverse spin splitter torque achieves charge-to-spin inversion efficiencies of 28%. These strong, non-relativistic responses allow altermagnets to generate giant magnetoresistance, the foundational mechanism for reading and writing digital data, with the exact same utility as traditional ferromagnets. This solves a highly specific engineering bottleneck in modern data storage: parasitic stray magnetic fields. Traditional ferromagnetic memory bits generate their own external magnetic fields. If they are placed too close together, those fields cause destructive crosstalk, overwriting adjacent data and severely limiting spatial density on the hardware. Engineers mitigate this by stacking complex synthetic alternating layers to manually cancel out the fields, adding significant manufacturing overhead. Altermagnets bypass this entirely. With exactly zero net magnetization, they generate zero stray fields, eliminating magnetic crosstalk physically. This magnetic robustness allows for significant spatial downscaling, bypassing the parasitic crosstalk that currently limits bit density in large-scale data infrastructure. Furthermore, because their internal spin dynamics are governed by strictly alternating structures, they switch states at terahertz frequencies, far exceeding traditional ferromagnets. They possess the ultra-fast terahertz logic speeds of an antiferromagnet and the sheer read and write utility of a ferromagnet. This precise combination provides the physical mechanism required to upgrade the limits of global memory infrastructure.